Hello dear students, welcome to the class and let's start today's session by doing the CBSE question pattern that you know that we have covered the chapter dual nature of radiation and matter. It's now time to check our ability whether we are able to solve the question which is from the reference book, from your NCERT books and the number of reference books. As you know, these type of questions, these kind of questions are those questions which you generally see in your board exams, in your reference books, in your sample papers and so many places where you see such questions. Here I have divided the question on the base of their marks. So, we are going to see the 1 mark question, 2 mark question, 3 mark, 4 mark and then 5 mark. This is the criteria that we have divided the question. Now, without wasting the time, let us see first question of the class. So, the question number 1 to 2, the instruction has been given that question number 1 to 2 is the 1 mark question. So, if it is a 1 mark question, you do not go into the detail of that, you just have to be at the point. You do have to give the point, the answer at the point. That means, firstly read out the question, the frequency of incident radiation is greater than the threshold frequency. Greater than the threshold frequency in a photocell. Then how will the stopping potential will vary if the frequency is increased, keeping other factors constant. Now, you know that we are having a relation of Einstein's photoelectric equation which is something like this, EV naught equals to h nu minus h into nu naught, where nu naught is your threshold frequency, h nu is the energy of photon and this EV naught is the energy of electron. Now, in the question, how will the stopping potential vary? This is the stopping potential. How will it vary if the frequency is increased, keeping other factors constant? So, that means if your nu will be increasing, what will happen? Okay, see here in this condition has been given nu is greater than nu naught. So, that means nu is greater than nu naught will coming out to be a positive term. So, that means you can directly see if V naught is directly proportional to frequency. If your frequency will be increased, your V naught will increase. So, there is a direct relation when nu that means frequency will increase, stopping potential will increase. Directly you have to give this answer, V naught will increase if we increase the frequency. Okay. Now, there is one more thing, answer is this much. You just for making you understand, I am telling you this thing. You know that when we are increasing the frequency of incident radiation, what will happen? The kinetic energy of the photoelectrons will increase. So, that means the electrons that are emitting out from the metal surface, they are coming with the high frequency, with the high energy. And to stop that to stop their velocity, that means the stopping potential that we are applying, more the energy with which they are coming, more the stopping potential we have to apply. So, again it is a direct relation, more the kinetic energy, that means more the frequency, because E equals to h nu. More the frequency, more will be the energy and more will be the stopping potential, right. So, this is how we can say this is the 1 mark question and there is a direct relation between the frequency and the stopping potential. Now, let us see what is the second question. Again a 1 mark question. In this question, if the frequency of the incident radiation is equal to the threshold frequency, incident radiation frequency equal to threshold frequency, what will be the value of the stopping potential? This we have to find out. Again, you know that what is the equation? The photoelectric equation can be written as EV naught equals to h nu minus h nu naught. Now, what are they asking? They are asking what will be the value of stopping potential. This is what? This is the equation of Einstein's photoelectric equation, right. Now, if you have been given nu equals to nu naught, you can do one thing, h nu minus nu naught. When nu is equals to nu naught, this term will become 0. So, that means EV naught is coming out to be 0, right. So, from here you can say that V naught equals to 0. That means at the very moment when your incident frequency will become equal to the threshold frequency, your stopping potential become 0. Okay, this is the answer of the question. That means V0 will be 0. Let us see the third question. Now this question instructs us that 3 to 4 questions are of 2 marks. There are 2 marks kind of question. A proton and an alpha particle are accelerated using the same potential difference. How are the de Broglie wavelengths lambda p and lambda alpha related to each other? See, we are having a relation with us at the very moment that I was doing the Davison-Germer experiment. I have told you I have derived one formula for you, that was lambda equals to h upon under root 2 m e into v, where m is denoting for mass, e is the charge and v is the potential. So we have been said that alpha particle and a proton, they are accelerated using the same potential. So that means V is same, but if I talk about the mass and the charge of alpha particle, that will be different. So let us say the lambda p, that means the wavelength of proton. We have to tell the de Broglie wavelengths of proton and alpha. So lambda p will be equals to h upon under root 2 mp, that means mass of proton, EP, that means mass of the charge of the proton, into V. If I talk about the alpha particle, I will be writing it like h upon under root 2 m alpha E alpha into V, right. Now you can do one thing, we know there is a relation between the mass of alpha particle and the mass of proton. We know that mass of alpha particle is 4 times the mass of proton, and the charge of alpha particle is the 2 times of charge of proton, because proton is what? Proton is nothing but 2He4, and we say that the charge is 2 times, the mass is 4 times of the proton, because proton is 1H1 and this is what? This is alpha particle, right. So this we have. Now we are having this relation with us, you can put this value m alpha and E alpha into this equation. So we will be having lambda equals to h upon under root 2 into m alpha is 4 mp, E alpha is 2 into EP, and V is same, because we are applying the same potential difference. This is lambda alpha. Now lambda p upon lambda alpha, because we want to find the relation between them, lambda p is h upon under root 2 mp EP into V. So put this value, multiplied by divide by lambda alpha. So lambda alpha is under root 2. So let's multiply this, 4 to the 8 to the 16. So directly put 16 over here, 16 into mp into EP into V divided by h. So cancel out the common terms, h cancelled, under root mp, under root EP, V, these will be cancelled. So we are having only under root 16 by under root 2. Directly you can write it as under root 8 or 2 root 2. So that means lambda p upon lambda alpha is under root 8. This is the relation between them, or you can write it as lambda p is equals to under root 8 times of lambda alpha. Okay. So this is the answer to the question, and this was the approach how to start this question. Okay. Let's see the next question. Again, how much marks? 2 mark question. 2 monochromatic beams A and B of equal intensity I hit a screen. The number of photons hitting the screen by beam A is twice that by beam B. Then what inference can you make about their frequencies? We have been given that there are 2 monochromatic beams A and B. of equal intensity I, they are hitting a screen, the number of photons hitting the screen A, that means Na, is twice that by beam B, equals to twice of beam B, right? This is the equation that have been given to us. And one more thing that has been given, that is equal intensity. Now if I talk about intensity of A, can you tell me what is the formula for intensity? I hope you are clear with the thing that how can we find out the intensity. Intensity is what? Number of photons coming with some energy. So that means IA, if I am talking about the intensity, number of photons of A multiplied their energy. Energy is h nu, so h nu A, because we are talking about intensity of A. What will be IB? That will be NB into h nu B. Now in the question it has been given this is equals to this. These two intensities are equal. Since IA equals to IB, I can write this as, okay. Now cancel out the common terms, H and H cancelled, and A nu A equals to NB into nu B. See, what we have to find, what inference can you make about their frequencies? That means nu A, this, and nu B. So if I will be taking an inference, nu A upon nu B is equals to NB upon NA. Right or wrong? Right? Now see, we have been given this condition in the question that Na equals to 2NB. So put this value of Na into this equation, so we will be having nu A upon nu B equals to NB upon Na. Now Na is 2 into NB. See, these terms cancelled. So nu A upon nu B equals to 1 by 2, or you can say nu B equals to 2 times of nu A. Frequency of B is 2 times of frequency of A. This is the inference that we have drawn from this condition that have been given in the question. Okay, so this is the answer. Let's move to the next question. Now instruction, question number 5 to 6, 3 marks. So we will be doing the question according to the marks that have been slotted for us. 5 to 6 is 3 marks question, so you have to start, and you have to start with the steps, because in the board exams you will be getting stepwise marks, right? So one wrong step you will be getting deduct marks. Ultraviolet light of wavelength lambda equals to 2271 angstrom. How can I write this as 2271 into 10 raised to the power minus 10 meter. From a 100 watt mercury source irradiates a photocell made of molybdenum metal. If the stopping potential is minus 1.3 volt, estimate the work function of the metal, and how should the photocell respond to a high intensity red light of wavelength 6328 angstrom produced by a helium neon laser. First of all, what we have to find? We have been given the wavelength, we have been given the source, that means 100 watt. 100 watt mercury source, it has been given to us. If the stopping potential is minus 1.3 volt. Now see, the minus 1.3 is itself showing that this is the stopping potential, because the stopping potential means the negative potential. So we can write this as 1.3 volt. Estimate the work function of the metal. First of all, we have to find the work function of the metal. Start doing the first part. We are doing up to this much first of all, then we will be moving further. From here, how can you find out the work function? Apply the Einstein's photoelectric equations. And you will be using this, you know that EV naught equals to h nu minus h nu naught. This h nu naught is nothing but your work function, because this nu naught is the threshold frequency. I am writing this as W, right? So, to find out the W, that means we have to do it like this. Okay. Now, h nu. Nu is not given, we have been given the wavelength. So, you can write this as h into c by lambda, because there is a relation between frequency and wavelength. Nu equals to c by lambda. You are putting this value over here and you have to. Okay, now what we else to do? The W, the work function equals to h. H is 6.6 into 10 raised to the power minus 34 joule second, that is value of Planck's constant, into c, that means speed of light, 3 into 10 raised to the power 8, divided by lambda, that is 2271 into 10 raised to the power minus 10, minus E into V naught. E, that means the charge of electron, 1.6 into 10 raised to the power minus 19 into V naught. What is the value of V naught? It is given as 1.3. So, solve for it, take your time and tell me your answer. When you will be telling me your answer, I will be writing the W, that means the value of work function over here, so that you will be having the value of work function and we can proceed further. Take your time, bring out the value of W now, and then I will start with the next part of the question. Okay. I thought you have taken your answer, you will be getting your answer, and by just using your calculator you can easily do this. So, when you will be putting the value and you will be getting the answer, it will be something like 6.665 into 10 raised to the power minus 19 joule. This is your work function, and you can also convert this value into the electron volt. How? By dividing this value of joule by 1.6 into 10 raised to the power minus 19. When you will be dividing this term by 1.6 into 10 raised to the power minus 19, you will be getting the answer in the electron volt. Okay. So, we have found a work function. Now, further what we have to find? How should the photocell respond to a high intensity red light of wavelength 6328 angstrom produced by a helium neon laser? We have to tell them that whether the photocell is going to respond towards this particular wavelength or not. To check whether this photocell is being responded towards this radiation, we have to find out first of all what is the threshold wavelength, because if the wavelength will be greater than the threshold wavelength, then if this wavelength, that means this, if this wavelength will be greater than the threshold wavelength, there will be no emission. That means photocell will not respond. Photocell will not respond. In case if the wavelength, that means this, come out to be less than the threshold wavelength, then the photocell is going to be respond, right. So, we have to check this condition. The photocell will respond only when this condition will be satisfied, when lambda is greater than the lambda naught. Sorry, photocell will not respond. When your wavelength is coming out to be greater than the lambda naught, that means threshold wavelength, photocell will not respond. It will respond only, photocell will respond. It is just opposite to the threshold wavelength, the threshold frequency, because in threshold frequencies your nu is greater than nu naught, then only the emission will take place, and in case of wavelength it is just opposite, because we are having the relation that is nu equals to c by lambda, that means nu is inversely proportional to lambda. See, we are having the work function as this. Now, to find out how can we write the work function? Work function can be written as h into nu naught, right or wrong, right. Now, nu naught can be written as again c upon lambda naught. Nu equals to c by lambda, nu naught will be equals to c upon lambda naught, right. So, put this value c upon lambda naught. From here what do we have to do? We have to find out the value of lambda naught. So lambda naught will be equals to hc upon w. Put the values over here. H is Planck's constant, divided by the value of w, that means 6.665 into 10 raised to the power minus 19. Again use your calculator to find out the answer. When you will be solving it, you will be having wavelength as 2980, right. This is the value that we have got in the angstrom. Now see, we have value of lambda naught equals to 2980 angstrom. Now we have to tell them whether the photocell will respond or not. We have to see this lambda naught and this lambda. So over here your lambda is coming out to be, let me just remove, your lambda is 6328 angstrom, your lambda naught is 2980 angstrom. Easily you can tell me this lambda is greater than the lambda naught. This value is greater than this, right. So what did I said? When lambda is greater than lambda naught, then photocell will not respond. So that means you can say photocell will not respond, right. And you have given the reason as well, because lambda is greater than lambda naught, that is why the photocell will not respond. And this is the answer of the question. Let us now see the next question of the session. Question number 6. The two lines marked A and B, these two lines in figure show a plot of de Broglie wavelength lambda as a function of 1 by root V, where V is the accelerating potential for two nuclei, one H2 and one H3. What does the slope of the lines represent? And identify which line correspond to these nuclei. That means these two nuclei, one H3 and one H2. So first of all, what does the slope of this line represent? You are having one equation with you, that means lambda equals to h upon under root 2me into v. You can represent this equation as lambda equals to h upon under root 2me into 1 upon under root v, right. Now compare this equation with this y equals to mx plus c. Which is your y axis? Lambda. Y on y axis you are having the lambda, and on x axis you are having the 1 by root v. See, this is your y axis and this is your x axis. So on comparing with this equation, your m, that means your slope, has came out to be equals to 1 upon m is came out to be equals to h upon under root 2me. Right. So the first question, the first part of the question, what does the slope of the line represent? You can give the answer, the slope of the line represent the h upon under root 2me. The second part, identify which lines correspond to these nuclei. Now see, the slope is inversely proportional to 1 upon root m. Inversely proportional to 1 upon root m. And now see which of these two lines is having higher slope and lesser slope. This A is having lesser slope because we define the slope in terms of angle. So see, this is having lesser angle and this B line has greater angle. So that means this is having lesser slope and B is having greater slope. So that means, and slope is inversely proportional to m. So that means if we are talking about A, which is having lesser slope, A line A is having lesser slope So it should have what? Lesser the slope, greater the mass. So if we are saying it represents the greater mass, so from 1h2 and 1h3, see 1h2 and 1h3, which is having the greater mass? The atomic number is same, the atomic mass is different. 1h3 is having higher mass. So that means this line A represent the 1h3, that means of higher mass, and B, which is having the greater slope, it will showing lesser mass, so it should represent 1h2. It should represent 1h2. Okay. This was the question. I think this was the easiest question which you are able to understand how we have done this question. Let us see the next question for the class. Question number 7. Okay, so now question number 7 is a 4-mark question. When the surface of a certain metal is illuminated with the light of wavelength lambda, the emitted photoelectrons possess a maximum kinetic energy of kmax. Show that when the light of wavelength this much is incident on the metal, the emitted electrons will have a maximum kinetic energy of 2 kmax. Start doing this with the relation that when lambda is falling, okay, do one thing. Start with the photoelectric equation. That will make the question easier for you. Einstein's photoelectric equation says that half mv square equals to h nu minus h nu naught. Earlier I was writing EV naught equals to h nu minus h nu naught. EV naught was the kinetic energy in terms of stopping potential, and here this is the kinetic energy in terms of velocity, that means half mv square. So this is the kinetic energy max. You can write this as kinetic energy max equals to h nu minus h nu naught, right? Now see, you can represent this as hc by lambda minus h nu naught. This is the kinetic energy max. This is say equation number 1. Now see what is the question saying. When the surface of certain metal is illuminated with the light of wavelength lambda, the emitted photoelectron possesses a maximum kinetic energy kmax. So that means kmax equals to hc by lambda minus h nu naught. Show that when light of wavelength dash, say this is dash, consider that this wavelength is lambda dash, okay. When this wavelength is incident on the metal, the emitted photoelectrons have a maximum kinetic energy of 2 kmax. So write this equation again in this form that if you are having the 2 kmax equals to hc upon lambda naught, sorry lambda prime minus h nu naught. Consider this as equation number 2, and this we have written using this particular equation. We have used 2 kmax in place of this, and in place of hc by lambda we have put the lambda prime. From here what we have to prove? We have to prove that lambda prime is equals to this particular equation. This we have to prove, okay. Now start doing that so that my lambda prime should be equals to that particular value. This is equation 1, this is equation 2. Do one thing, subtract these two equations so that you will be having 2 kmax minus kmax, that means 1, 2 minus 1, 1. So kmax equals to what? hc upon lambda prime minus hc upon lambda minus h nu naught plus h nu naught. These two will be cancelled. You are having hc by lambda prime minus hc by lambda. From here bring out the value of hc by lambda prime. Kmax minus plus hc upon lambda. Hc upon lambda prime equals to k max plus Hc upon lambda. So, do one thing to find out the value of lambda prime. This is lambda into k max plus Hc upon lambda, right. From here you can easily find out the value of lambda prime. Lambda prime will be equals to what? Lambda hc, lambda prime will be lambda hc upon lambda k max plus hc. We have proved this value. Now we have to check whether this is the same that has been given or not. Lambda hc upon lambda k max plus hc. Lambda hc upon lambda k max plus hc. So, we have proved it, and yes, this is the wavelength. We have to show that when light of wavelength this is incident, we have the kinetic energy of 2 max. So, this we have proved, that means we are reached to the correct point. Start doing the next question. Question number 8. Illuminating the surface of a certain metal alternately with the light of wavelength lambda 1 and lambda 2, where the condition is lambda 1 is less than lambda 2, it was found that corresponding maximum velocities of photoelectrons differ by a factor of n. The corresponding maximum velocities of photoelectron. So, if one is having the velocity of v1, another is having the velocity of v2, so we have been given the situation that v1 upon v2 equals to n. This is the condition that has been given. Show that the work function of the metal is given by this particular equation. Start doing the question, start using firstly the Einstein's photoelectric equation. In this chapter, this is the important equation. Without knowing this equation, it will be harder for you to understand. Or you can write this h nu naught as W, that means the work function. Firstly, we have been given the lambda 1 and then we have been given the lambda 2. So, half mv square, let me just write half mv1 square equals to hc by lambda 1 minus W. Because this is the same metal, so work function will remain same. So, hc upon lambda 1 minus W, this is your equation number 1. Second equation will be half mv2 square equals to hc upon lambda 2 minus W. This is your second equation. Now, what you can do? You can divide these two equations. After dividing, you will be left with v1 square dividing 1 and 2. v1 square upon v2 square equals to hc upon lambda 1 minus W upon hc upon lambda 2 minus W. Now, see, in the question we have been given v1 upon v2 equals to n. So, you can put the value of v1 upon v2, that is n square, because it is here v1 upon v2 square. So, n square equals to hc upon lambda 1 minus W minus divided by hc upon lambda 2 minus W. You can do one thing, you can multiply this n square into hc upon lambda 2 minus n square W equals to hc upon lambda 1 minus W. So, do one thing, bring out the common terms and take the common terms together. This is lambda naught square, this is 2, lambda 2 minus hc upon lambda 1 equals to n square W minus W. From here you will be having, bring out the common, that is W over here. So, you will be left with n square and minus 1 into W equals to what? N square hc can be taken as common. So, 1 upon lambda 2 minus 1 upon lambda 1, right. So, now what you can do? You can take out the value of W from here very easily. n square hc, you will be having lambda 1 minus lambda 2 upon lambda 1 into lambda 2. So, W from here will be equals to n square hc lambda 1 minus lambda 2 upon n square minus 1 into lambda 1 into lambda 2. Now, let us just check whether this is correct or not. So, n square hc into lambda 1 minus lambda 2, n square hc minus lambda 1 by lambda 2 upon lambda 2 into n square minus 1. You can do one thing, you can take out you can divide the whole term by lambda 1. So, that means you will be left with, okay, we have to bring out the answer in terms of what we have been given. Let me just write this complete term in that side so that it will become easier for me to convert the situation into that we have been given in the question. W equals to n square hc into lambda 1 minus lambda 2 divided by n square minus 1 into lambda 1 lambda 2. Okay, hc, n square hc. When you can see over here n square minus lambda 2 by lambda 1. When you will be solving it, you can easily convert this particular situation into that form that has been written over here. How you can do that? When you will be dividing this complete term by lambda 1, so you will be left with 1 minus lambda 2. Okay, that we can't do. This is lambda 2 by lambda 1. So, you can easily modify this by using your own tricks. We have reached to this particular situation, and by reaching to this point, this has become very easier for us, because starting from that and reaching up to here, we have to do some modifications that you have to do by your own, and you will get your answer very easily. I have tell you the approach, reach up to the correct answer. Okay. So, now come to the next question, the question number. And yeah, in this particular question we have been given that lambda 1 is less than lambda 2. So, here it is given lambda 1 minus lambda 2, it cannot be the correct, because then the work function will come out to be negative, that cannot be possible. So, find out that thing where you will be having your lambda 2 minus lambda 1. Draw the suitable graphs to show the variation of photoelectric current with the collector plate potential for a fixed frequency but different intensities. L1 is greater than L2 is greater than L3 of radiation. In second part, a fixed intensity but different frequency. Let me tell you that this is the important graphs of the chapter that you have to learn by your own, and you have to basically understand. If you understand, you can make the graph very easily. I am going to tell you one trick that will make this concept easier for you to understand. Firstly, we will be drawing the graph plotted between the collector plate potential here it is negative, here it is positive. We are drawing the graph. On x axis we are taking the collector plate potential, on the y axis we are taking the photoelectric current. So, first part is a fixed frequency but different intensities. Now, see, if we have been given the different intensities, that means I told you when the intensity is changed, the number of photoelectrons that are emitting, that will be affected. More the intensity, more the number of photoelectrons, and so more will be the current. So, that means if your intensity is being changing, your current will be changing. So, do one thing, if you want to change the current, you have to let me draw it neatly. The graph is correct, but neatness is not there. So, you can do one thing, you can make it like this. See, these are three intensities. I3, where the L1 is greater than L2 is greater than L3. So that means L1 is maximum, L1, L2 and L3, and they are reaching to a same potential, that is V0. Now see, the trick that I want to tell you, when you have to plot a graph between I and the collector plate potential and the intensities has been given to you. So at that time you have to understand that when you will be having different intensities, you will be having different current. Different intensities, different current. I for current, how do we denote the current? We denote the current by I, and intensity. Intensity is being started from the first word, that is I. Intensity is I, right? I is changing, this current is changing, intensity is changing, that means I is being changing, so the current I will change. The intensity is changing, current will be changing. This is the trick to remember, I, okay. The second thing, a fixed intensity but different wavelength. For that, again we will be drawing the graph. This is collector plate potential and this is photoelectric current I. Now see, I told you that when you are having the different frequency, that means here it was you are having frequency fixed, nu is fixed. In second graph you are having L constant, L is fixed. Now see, a fixed intensity but different frequencies. More the frequency, more will be the kinetic energy of the photoelectrons, and so more will be the stopping potential. I told you in the very first question we have solved in 1 mark question, more the energy, more the frequency, more will be the energy, more will be the stopping potential. So that means if this is the graph for L constant, this we have with us, which is showing the different stopping potential V01, V02 and V03. In the question we have been given nu1 is greater than nu2 is greater than nu3, nu3, nu2, nu1. So that means if you are having these different frequencies, so that means different energies, and since different energy is there, so you have to apply different stopping potential. Okay, so you have to learn these graphs by heart. Now let's move to the next question, that will be the last question of the session. It is a 5 mark question, and in this question we have to explain what do we mean by a photon. So let me just simply tell you what do we mean by the photon. It is a quantum of electromagnetic radiation. What does it mean? It is a quantum of electromagnetic radiation. This you have to write over there. And secondly, why most electrons are emitted with the kinetic energy less than the maximum. See, when the photons are being falling over the plate, the electrons are getting emitted. The electrons that is getting emitted, they are coming from the inside of the metal surface. So that means when they are going from the inside, the energy is being wasted in bringing the electron from the inside to the surface of the metal. When it will reach to the surface of metal, half of the energy will then be used in emitting of the electrons, right. So that is why the electrons are not being emitted with the kinetic energy that is being provided by the radiation. That is why it is coming with the lesser kinetic energy. Why? Because half of the kinetic energy is being used to overcome the force that is being applied inside the electrodes. B part. The photoelectric effect provides evidence for the particulate nature of electromagnetic radiation. State 3 experimental observations that support this conclusion. So first of all, you can write that the photoelectric process is an instantaneous process. Secondly, you can write the photoelectric process will only happen when you will be having the frequency greater than the threshold frequency. Thirdly, you can write because we have to give the three experimental conclusion. Thirdly, you can write if you are giving the, if the frequency of the radiation is more, the kinetic energy of the electrons coming out will be more. And if the number of photons falling over the surface will be more, the intensity is more, the number of photons that will coming out, that will be more. Okay. Then the third part, electromagnetic radiation of wavelength lambda and intensity I when incident on a metal surface causes n electrons to be emitted out per unit time. The maximum kinetic energy of the electrons is Emax. State and explain the effect, if any, on n and Emax. So, we have to tell the effect on n and Emax when the intensity is reduced to I by 2. See, the intensity is reduced to I by 2, that means the number of photons, that means coming out, number of photons will be reduced to n by 2, right. Now, since n is reduced to n by 2, what do you have to check here over here? The intensity is reduced to I by 2, but the wavelength is unchanged, and you have to tell the effect on n and Emax. So, you will say when I is reduced to I by 2, intensity is reduced, so n will be reduced to n by 2, but since the wavelength is not changed, so that means kinetic energy or Emax will not be affected. So, in first case we are having two things, n will be reduced to half, Emax will not get affected. Second part, the wavelength lambda is reduced but the intensity is not changed. When lambda is reduced, energy will be what? E equals to h nu, or you can write it as hc by lambda. When lambda is reduced, energy will be increasing, because this is the inverse relation. So, energy will increase, but intensity is not changed. When intensity is not changed, so number of photons will not change. So, two things, number of photons will not get affected, energy will increase. This is the case of first, this is the case of second. So, we are done with all the questions that can be arrived from this chapter. I hope you understand all the question, all the concept. Keep practicing, keep revising such type of question, and take the more and more number of reference books and sample paper to solve the question, because these are the questions that you will see in JEE Main and JEE Advanced, NEET also. Important chapter it is. So, keep practicing. Take care. Thank you.